This is an example problem I created on momentum to hit on a bunch of different problems and ways to solve problems that you guys need to do as you prepare for your exam here on momentum. We started this problem in class. I thought I'd do a work-through version for you guys to follow along. We have a Tesla Model S with a mass of 2,000 kilograms speeding down the highway at 40 meters per second, approaching a slower-moving Honda Civic with a mass of just 1,200 kilograms. Traveling at just 25 meters per second. Due to malfunction, the Tesla does not apply the brakes and collides with the Civic. After the collision, this Tesla is traveling 33 meters per second. How fast is the Civic now going? So, like most problems, let's start with a picture. All right, initially, you've got one car. We got the Tesla moving along with a velocity, and we're moving at 40 meters per second, and they run into the Civic. And the Civic is moving along in the same direction at just 25 meters per second. This is our initial scenario. This is before the collision. Later, or our final scenario, you now have the Tesla, probably with a little beat up front end, is now traveling just 33 meters per second. And something must have happened to the Civic, which now has a beat up front end, and probably got a boost. But we don't know how fast that Civic is going after the collision, right? So here's our before and after situation. They didn't tell us what type of collision this was. Was it elastic or inelastic? If they told us it was elastic, then you can use energy and say that the energy was conserved, in this case, kinetic energy. But since you don't know anything about what kind of collision, elastic or inelastic, we can't use energy because energy is almost always lost in a collision. So instead, we're going to use conservation of momentum, which says that the momentum of a system initially has to equal the momentum of the system later, or really before the collision and right after the collision. Well, our system in this case is the two cars. So really you have the momentum of the Tesla at the beginning plus the momentum of the Civic at the beginning has to equal the momentum of the Tesla at the end plus the momentum of the Civic at the end. And these momentums are all used with the equation P equals mv. So you can say that the mass of the Tesla and the velocity of the Tesla at the beginning plus the mass of the Civic, the velocity of the Civic at the beginning, has to equal the mass of the Tesla, velocity of the Tesla at the end, plus the mass of the Civic, velocity of the Civic at the end. So you really derived this more complicated equation from really P equals P at the top, conservation of momentum. Momentum is always conserved in a collision between any two objects. What is not always conserved is the energy, but we can always use conservation of momentum. So now when we plug in the numbers we have, all of my arrows point to the right, which makes this problem a little bit easier. I can write in the mass of the Tesla, 2,000 kilograms. Its velocity initial is to the right at 40. It's a good habit to put the sign with the number, even though in this problem it doesn't end up mattering. The Civic is moving to the right at 25 meters per second. Later, you have the Tesla has slowed down. It's only 33. And you have the Civic moving at some final velocity. And so when you work this problem out, you're looking to solve for your V final. You have 2,000 times 40, which is 80,000, plus 25 times 1,200, which is 30,000, is equal to 2,000 times 33, which is 66,000, plus 1,200 V of the Civic final. So on the left side, you have a total of 110,000. If I add those together, 80,000 and 30,000 is equal to 66,000 plus 1,200 V Civic final. Algebraically, I would subtract 66,000 from 110 and get 44,000 is equal to 1,200 V Civic final. And when I divide by 1,200, I get a velocity of the Civic at the end. It ends up being a positive value. Well, it should be. My arrow's to the right, of 36.67 meters per second. So that's how fast the Civic is going after the collision. It makes sense. It got rear-ended. It should be going faster than what it was. It was going 25. Now it's going 36, so it's sped up. So the question to follow up is, well, now that we know the velocity, what was it, elastic or inelastic? And the difference between these two is really, is the kinetic energy of the system conserved? That's really what we're asking. And what we mean by that is we're asking ourselves, does the kinetic energy of the system at the beginning equal the kinetic energy of the system at the end? That's our question. Well, now that we know the masses and the velocities, and we know that KE is equal to 1/2 mv squared for any object, we can find the energy of the system at the start and compare it to the energy of the system at the end. And so we're going to look at the kinetic energy of the system at the beginning, and that's just the kinetic energy of the Tesla at the beginning plus the kinetic energy of the Civic at the beginning. And that's just 1/2 the mass of the Tesla, velocity of Tesla at the beginning squared, plus 1/2 the mass of the Civic, velocity of the Civic initially squared. And we know those values. All right, that would be 1/2 of 2,000 times 40 squared, plus 1/2 of 1,200 times 25 squared. And you get a big number. Should be a lot of joules of energy with these fast-moving cars. Plug it into my calculator. We get 1,000 times 40 squared plus 600 times 25 squared, and I get 1.975 million. So 1,975,000 joules. That's our energy before the collision. Well, let's figure out what it is afterwards. And so all I need to do is calculate with the velocity I just calculated for the Civic. So the system at the end is just the same equation except with the final velocity. So the Tesla at the end plus the kinetic energy of the Civic at the end. I'm just going to go right into plugging in the values. That's 2,000. This Tesla is only going 33 now. So that's the new velocity. And the Civic, 1/2 of 1,200, and we had 36.67. Depending on how you round, you might get slightly different values. And when I plug that in, get 1,000 times 33 squared plus 600 times 36.667 squared, and I get 1.896. 1,896,000. I rounded slightly. All right, that's our kinetic energy at the end, right? Before or after. And with that the case, it looks like we lost some energy. Those values are not the same. If I take 101,975,000 and I subtract the value I got, now my calculator I have it stored, and so I have the exact value. We can actually subtract and find a value for the energy lost. All right, there are 79,300 joules lost. All right, that's the difference in the energy before and after. So if I ask how much is lost, you just subtract them. But since I've asked, is it elastic or inelastic? Well, we lost energy, so we know that it is an inelastic collision. All right, because energy was lost in the collision. All right, let's take it a step further. Now we're asking, well, what is the impulse on the Tesla? All right, well, an impulse is simply a change in momentum. All right. Also delta P, which really is just the momentum at the end minus momentum at the beginning. Well, let's look at the Tesla. The momentum at the end would be its mass times the final velocity, and the momentum at the beginning would be its mass times the Tesla's initial velocity, which is simply mass of the Tesla times its change in velocity, right? V final minus V initial, which lo and behold would be m times delta V, right? The change in velocity. And let's plug in what we have. The mass of the Tesla is 2,000. It finishes going 33. It started going 40. And so it loses 7 meters per second. And so 2,000 times 7, it ends up losing 14,000 units of momentum, which are kilogram meter per second. That's its impulse, right? Its change in momentum. Now, what should it be on the Civic? Well, we could calculate it the same way, right? The Civic would be the Civic's mass and the Civic's final velocity subtracted by the initial, which you get 1,200. It finishes going 36.67. It started at only 25. And you're going to have some rounding errors that I don't even need a calculator here. I should get positive 14,000 kilogram meters per second. Now, in my calculator, if I type that actually in, 1,200 times 36.67 minus 25, I actually get 14,004 in my calculator. Now, why do I know that's wrong? Well, momentum is conserved, right? Conservation of momentum. If one loses momentum, the other must gain it. The Tesla lost 14,000, which meant the Civic must have gained it. Now, if I didn't round, if I carried out all those sixes in my value, I would get exactly 14,000 for the Civic. But I get a little bit more because my calculator has some rounding errors. But you get about the exact same thing. And now, if the collision took place over a time period, we can actually look at the force, right? We're given a time, we want a force, and we know that the change in momentum is equal to the force times the time. And so if I want to know the force they feel, force would be the change in momentum over time. And so the force on the Tesla would be the change in the momentum of the Tesla over the time, which was negative 14,000 over 0.05. And so if I take 14,000 divided by 0.05, I get the 280,000, negative 280,000 newtons. We're now in forces. And the Civic, I hope we don't need to do that calculation because notice the values are the same, but with a positive, which means we have the same force. Well, I think Newton would agree with us, right? This is the third law. Equal and opposite action-reaction pairs. So this actually makes sense, right? If the Tesla is applying a force on the Civic, then according to Newton's third law, the Civic is applying a force right back on the Tesla. It's just in the opposite direction. And so again, we've called to the right positive. And so the force acting on the Tesla would be slowing it down, pushing left, which is why it's negative. And the Civic is experiencing one to the right. Lastly, let's look at G's. This is just to kind of connect to something we already know. G's is sometimes referred to as a G-force. Sometimes it's an acceleration. So really what I want to know is what is the acceleration of the Tesla? Well, that's going to be equal to, well, F equals m times A. So A should be F on the Tesla over the mass of the Tesla. All right, so the acceleration is going to be that 280,000 newtons over the mass, 2,000 kilograms. Newtons per kilogram, remember that unit? That was field strength due to gravity, which is also meters per second squared. So if I divide 280,000 divided by 2,000, I get 140 newtons per kilogram, or meters per second squared. Now, comparing that to gravity, a G, if I want G's, I just take, all right, the actual acceleration and divide it by the acceleration due to gravity. All right, remember, if I wanted the G force, well, it would be the force applied over the weight, Fg. Well, isn't that just the mass times acceleration over mass times Ag? Notice the mass cancels, so you get the same ratio, whether you look at it as a force or an acceleration. And so the G's on the Tesla is going to be 140 meters per second squared over 9.8 meters per second squared. And so this is a really good way to give an idea of what people actually feel in a collision. This is going to be 14.3 G's for the Tesla. Now, what about the Civic Driver? Well, they experience the same force. Do they feel the same thing? Well, for the Civic, that's going to be the force on the Civic over the mass of the Civic. However, the Civic has less mass and experiences the same force. Its mass is only 1,200, which means we actually have a greater acceleration. We have an acceleration of 233.3 meters per second squared, which means the G's would be 233.3 over 9.8. If I divide that by 9.8, you get a bigger amount of G's, 23.8 G's. If you're the driver in the Civic, you're possibly injured. You're experiencing a large number of G's. Now, that's probably enough to get some whiplash, maybe a head injury or a concussion. If you get around 50 G's in that time period, that can kill you, depending on what part of the body it strikes. But obviously that Tesla driver in a much more massive car had a much smaller acceleration overall, even though experiences the same force. It's, again, a good reason why being in a bigger car is better when you're in a collision with another car. You're going to accelerate less due to your larger mass, even though you guys are experiencing the exact same forces in that impact. So it's just a really good example, kind of tying everything together for a problem where we have two cars colliding using conservation of momentum, find the velocity of a car, determining the energy lost in the system to determine whether it's inelastic or elastic, transferring that into what an impulse is, its change in momentum, and how the forces come into play when you have the time of impact. And again, if I increase the time, I decrease the amount of force overall. So a longer time, that's where the crumple zones come into play with cars. We want to increase the time of the impact. So hopefully it's a pretty good summary. Spend a little bit of time kind of relearning this stuff, and hopefully it gets you ready moving forward.